Okay, so first of all, thank you for inviting me. And my name is Mijat Kustudić. I am from Serbia, but I'm a third-year PhD student from the Shenzhen University in China, and I'm really happy to be here, even though we're online. And I like exploring these artificial societies and agent-based modeling. So I got interested in this. I finished economics and I got interested in this topic because I think we can, in a way, predict what's going to happen in the real world. So this is a paper I wrote for Scientific Reports, Nature. It's called Agent-Based Analysis of Contagion Events According to Sourcing Locations. So what I did is I explored the basic concepts of how disease spread. So these are the table of contents, and I will just start with my topic. So what there was during the COVID-19 pandemic and is already happening is there are and were numerous predictions regarding the length of the pandemic. And, you know, I read a lot of papers regarding this topic, and I figured after a month, 3 months of reading that we cannot predict what's going to happen. We don't know when exactly the pandemic is going to be over. So there's a lot of research, and almost all of them give different predictions. But you know, someone will eventually get things right. Someone will say it's going to last for 3 years and it's going to happen. So if we have such prediction capabilities, wouldn't it be easier to predict soccer matches? I mean, it has simple rules, simple interactions, and only 22 players. And the world pandemic has COVID-19, a lot of different diseases, a lot of like 7 billion people. You cannot really predict it. So what I realized is we should, or I should, analyze basic principles of how disease spread. And my idea is to keep the rules simple as possible. Basically follow the KISS principles, which is keep it simple, stupid, which means that you just input the basic things into the simulation and get the basic output, which is, you know, like Occam's razor, which means the simplest solution or the simplest explanation is most probably right. So what we did is we took the basic concepts of the first human was infected by COVID-19 from Wuhan, China. But the problem is that the research also shows that there's a lot of different viruses found in different mutually distant areas. So let's say Wuhan is somewhere in middle of China, but there's a lot of viruses near Vietnam. So what if the virus started from Vietnam? How would the epidemic spread? Would it spread slower, quicker? What is the population? And all of these things. So that got me thinking. So the best way to approach this topic is basically just use agent-based modeling and programming with a lot of different inputs, like the basics of economy and so on, to get the right solution. So as I said, what if the virus originated in another location? And how will future waves of epidemics behave if they originate from a different location with a different population? So, as I said, agent-based modeling is a way to go. So, what we do is we implement agent-based complemental and reservoir arrangement of fractal cities. So, this means that we create cities, use intelligent agents that move around them in a reservoir setting. All cities radiate gravitational social attraction based on a Zipfian distributed population. And we implement fractal dimensions and lacunarity to analyze event probability and its consequences. So yes, this is a lot of things, but I will put it simple in pictures. So, you know, you live in a city where you mostly meet people. The city, I don't know how much people it has, but you mostly meet the same group of people. So you mostly talk with your colleagues and your friends, neighbors, family. So you have a limited amount of people you talk to every day. And the basics of compartments in epidemiology is you have three possibilities. So people are susceptible, people are sick, or are cured. So you have either you are sick, either you can be sick, or you aren't sick because you have passed through the previous two compartments. So what we have is we have created the situation with, this is the fractal observation of cities. So the basic things of fractals is basically dimensions. So there's a lot of dimensions that happen. Let me just, okay, this. So you have these individuals, you can be one of these three steps, S, I, or R. And then, okay, so then you get to the higher level, which is subpopulation. So let's say these are your friends or are just some people that people usually meet. And then from that point above, you have the meta population, which is a bigger group of those people. So let's say a couple of families living in a building are a meta population. And then you have a thing which is connected like a community, and then from a community you have a building block, and then from a building block you have a city center, and then from then on you have a large city, and so on. And then you create the whole country. So, oh, sorry. Let me just delete this. Okay. So how we did that? The basic thing is how to create the world where our agents live. So as I said, we tried to keep it simple to get the best and probably the most accurate results. So what I did is I created this small community of people. Basically, as I said, maybe 10 people, maybe we hang around with 10 to 15 people. Of course, some people with more, some people with less. And then you create a city from a lot of these people and communities. And then all of these cities radiate gravity. So gravity is basically the more people there are in a city, more often other people are going to move in that city. So a lot of people are going to come to Moscow. And if you are living in Moscow, probably you aren't going to go to a smaller city. So it's always people like to move to the bigger city just for business, because there's a lot of offices, there's a lot of businesses, a lot of money. And if you're already in Moscow, you're not going to go to a village. Because like there's nothing to do there. It's not so interesting. So you create this city, then you create a lot of them, different ones, different sizes, of course, and all of them radiate gravity. Of course, bigger cities have a greater gravity, smaller ones have a smaller gravity. And of course, I let them be connected to each other with roads. So people can move, of course, but it depends how interested you are in moving across cities. So then this is how the map looks like. I took three different types of cities. You have like, let's say the countries. You create a perfect country with 10 cities, like everything's perfectly connected. You have a broken, let's say broken up country. And then you have a medium connected country. So to simulate how the disease spreads if you have a good infrastructure. And then you have a largest city population of 10,000. And then the Zipfian from Zipf, that's a distribution where the biggest city has the most population, but the smaller ones have less and less and less, of course. And then, so what are the simulation results? So I use that for 350 iterations, 10,000 people in my agent-based model. And I check to see what the simulation results are. And then I got that this is basically what happened. Of course, the basic thing is I start the simulation from the infection from either the smallest city or the largest city. And here up, let me just draw. So we have starting from the smallest city here, or the largest city. And of course, it depends on the country. Either you have a perfectly connected country, broken off country, or like even worse off country. And then these are the simulation results. And these are just like infection things. So you see that the disease spreads the fastest if you start from, if it's in a perfectly connected country. And if the country is a bit isolated, then the disease starts spreads slower. So basically, if you have a disease that starts somewhere in Siberia, it would be spreading slower than if it started from Moscow, of course, because if you live in the middle of Siberia, there's no railroads, there's no cars, it's, you know, basically isolated. So that's what you see on the middle and the right part of the picture. But okay, so then I realized that, okay, we should plot this per city. So see what's happening inside the city themselves. And of course, there's something I should mention, which is the honeymoon effect, which I saw happening. The honeymoon effect, which is a jump when infected advance from a small reservoir to a new, larger one. So what does that mean? Also, the disease, whatever it is, let's say COVID-19, will eventually stop, or it will not. But what we need to do is we need to resolve the disease in a couple of ways. Either everyone gets vaccinated, or everyone gets infected and moves from the eye compartment to build up their immunity by getting over the disease. And then the disease will not have anywhere to spread. So the problem is, if you constantly put people in quarantine, if you close off the country over and over and over again, the disease can move unlimitedly, because, you know, people will not have an immunity, and only one person can restart the whole situation. So then you have a problem. So either let everyone get infected, or vaccinate everyone. So this is basically what the honeymoon effect says. So this is how it looks like. And this is the most interesting part. And I will compare it with the real situation. So you have the smallest city. You have look at this. So basically, you need to search for the gravity. As I said, people in small populations in small cities will move to bigger ones. So see, okay, so let's start from the largest city. See how from here, basically to here, the infection is inside the largest city, and here also, and here also. So the gravity keeps the infection inside a city. But here on the top side, you have that infection is spreading much more quicker, and because you see how this line and here, this is like this and like this and so on. So here it spreads quicker because people move from a small city to a larger one, and then the larger reservoir gets infected, and then you have a big problem. So this is what I got from my agent-based modeling approach, that it's much worse and the disease spreads quicker if it starts from a smaller reservoir.
And if it's from a bigger reservoir, like a large city, it keeps contained inside the city. So, okay, so this is the smallest and largest city. Numerical results, which you can find in my paper. So basically everything says that it's worse to start from a smaller city. And let's check it out with the real world results, and we will find something quite interesting. So to test our hypothesis, I implement the data from Sierra Leone and Liberia and two diseases, Ebola and COVID-19. So Ebola started in rural areas with a small populace, while COVID-19 started in China and was imported to their largest city, because largest cities in those countries have airports. So I was searching for two diseases, I was searching basically for one disease, but the disease should be relatively simple, similar to each one, and not a lot of time should have passed between two diseases, but that's quite difficult to find. So I said, okay, Ebola and COVID-19 in Sierra Leone and Liberia, because they were hit 6-7 years ago was Ebola, and we have COVID-19 now. So not a lot of time has passed, and there are some differences between the diseases. So here you can see that how Ebola and COVID-19 spread. So as I said, if it starts from a smaller populace, like Ebola, you see how it jumped really high and how infectious it was here in both Sierra Leone and Liberia. And COVID is not so, it is in the main country, in the main city, capital city, but it's not so dangerous as Ebola. So on the next slide, as I said, pathogen differences. So Ebola is transmitted by blood or secretions, and COVID-19 is considerably more transmissible. You can speak or cough and infect someone. Ebola patients are not contagious until they develop symptoms, and Ebola is more lethal than COVID. So basically, everything points to COVID-19 should have spread quicker and more dynamic. But on the previous slide, you saw that it's not what happened. But interesting thing is, when you look where it started, so one started, as I said, in large locations and small locations. So small locations is for Ebola, large locations is for COVID-19 through the airport from China, let's say. So this is the best part, which I really got interested to. I was really surprised what happened. So you remember the last photo, the slide a couple of slides ago. So you have COVID-19 and Ebola. Ebola is here. So just a moment. Okay, so this is the large location. And this is the small location for Ebola. And you can see that on the COVID-19, how the gravity of the large location of the capital city keeps the infection inside it. And on the other side, Ebola, you have the small population, but the reservoir got filled up quickly. And then the disease started spreading from that small filled up reservoir to other cities. And a lot of people, because there's nothing to do basically in the jungle, they need to move around the country to larger locations, but the larger locations have a bigger populace. So then because of that, they just spread around and infect more people. So basically, that's one of the interpretations what happened in and what can happen in the future regarding different diseases. So of course, you can check the numerical results and this, based on real data sets. And basically they show the same thing, that it's much worse to start from a small population. And also a couple of other conclusions from other papers.
research shows that connectivity matters more than density, which is, of course, if you have, as I said, that's why I tested the perfectly connected country, which with another not so connected country. As I said, like Siberia is not well connected and disease will stop there. Of course, large cities have a greater probability to become large spreaders because there's a large community living there. And of course, what is also interesting is if you have a country that is connected by land to another one, for example, Italy, borders are much more porous. So there's a lot more people going from one country to another if we have a border, land border, than if they're coming in by air. So that's one also a big difference. And of course, the gravity is, I think, the main thing. So those are just like conclusions from some other papers, and you can also check my paper for much more detailed explanations of these things. But I think that this is, just like a picturesque explanation of what I found, of course, by implementing artificial societies. And I think it's quite interesting, and I hope you liked my presentation and my paper. Thank you.
Yeah, thank you very much.